In this video, we're just going to look at some of the big concepts in terms of some word problems and also area. Okay, so just kind of a review. Miss McKenzie runs along a path with a velocity in feet per second at time t given by the equation you see there on the interval from 0 to 2 pi. Now, that's kind of an ugly equation. I don't expect you to have to do that one by hand. So I did pull a graph up. Let me just kind of expand it here. This is a graph of that equation from 0 to 2 pi. So you can see the zeros at 2.074 and 4.488. And having done some of these velocity problems before, I think you probably guessed that those are going to be important. So let me shrink it back down so we can read the problems. First, when is Miss McKenzie moving to the left? Well, moving to the left, or backwards, remember, is when the velocity is less than 0. So looking at that, that looks like that's from 2.074 to 4.488. Okay. When is Miss McKenzie moving to the right? So that's when the velocity is greater than 0. So that's from 0 to 2.074 and 4.488 to 2 pi. Okay. Now, there are other questions we could ask here. When does Miss McKenzie change directions? Of course, that's when velocity changes signs. Now, total distance and total displacement. One of these two is just the integral, okay? And that is displacement. Displacement is just going to be the integral from 0 to 2 pi of velocity. Okay? And, I'm not going to necessarily type that in. I think it's about 32 if you want to. You could just use FN int. But displacement, says how far is Miss McKenzie from where she began. Total distance, the only difference there, we still do an integral, but we do the absolute value of velocity, like that. Okay, so that's the difference between the two. Distance is the absolute value of velocity that we integrate. Displacement is just integrating velocity. Now, average velocity. Couple ways you could think about this. Average, we could say, well, velocity is distance over time. So if I knew how much total, movement or displacement there was, and just divided that by time, and the example would be if Miss McKenzie ran 100 feet in 20 seconds, then her average velocity was 5 feet every second. Okay, so we just figure out how far she went and divide it by how long it took. Well, that of course would be this answer right up here, and as I said, I think it's about 32 or 33, and then we could divide that by 2 pi. But I wanted to kind of remind you of the more calculus way to look at this, and that's to do the average value. Okay, we have a velocity equation and we want its average, so we find the average value of velocity. But I want you to look and see how these are really just stating the same thing. We said if we found out how far Miss McKenzie went, which the integral would do, that's what the integral will do, then we divide that by how long it took. Well, here we're dividing by 2 pi. So these are equivalent. Okay, these are the same thing. Of course, that should make sense. But we had looked at a very geometric representation of average value, looking at rectangles and the height of a rectangle. This is the more real-life application. And you can start to see that, if we want the average velocity, instead of actually having to, kind of calculate something, we could just set it up as average value. Okay? The one other thing I wanted to look at here was the area bounded by y cubed minus y squared and 5y squared. And you can see I have a graph here. This was by Desmos. That's a great free app. Let me just write the title down there if you're ever looking to have something on your iPad or iPhone that is really, really nice. But of course, on your calculator, you can't really get a graph of that. So I'm gonna do it by hand, and we'll just kind of verify with the graph. So of course, we need the intersection points to set up our integral. So I'm going to set the two equal to each other. I'd subtract 5y squared from both sides. I'm going to factor out a y squared. So 0 and 6 are my zeros, so that is what will make, those will be the bounds of my integral. Okay. Now you can see that, I hope, that, we've got the parabola, we've got the cubic, and in terms of y, 0 and 6 are the bounds. Remember, we're doing this in terms of y, so 0 and 6. Okay. Well, next, we want to know what function's on top. I would pick an interior point, maybe 1. Plug it in. 1 cubed minus 1 squared is 0. 5 times 1 squared is 5. So the parabola is on top, and you can see that that's true. The parabola has the bigger value. The blue has the bigger value. So we're going to have 5y squared minus y cubed minus y squared. You want to put that in parentheses so you don't miss any signs. Okay. Now let's do the antiderivative. So we got 5/3 y cubed minus 1/4 y to the 4th plus, because it's minus a negative, right? Minus a negative right there. So plus 1/3 y cubed, evaluated 6 and 0. Now before I evaluate, because if we're doing this by hand, sometimes it's nice to maybe do a little combining. You look at this, 5/3 y cubed, 1/3 y cubed. Well, that combines to 6/3 y cubed, or just 2y cubed. It might be nice to just write that. Just say it's 2y cubed minus 1/4 y to the 4th, evaluated at 6 and 0. Now if I plug in 6, I get 2 times 6 cubed. 6 cubed is 216, so I have 432 minus 1/4 y to the 4th. So 6 to the 4th divided by 4, probably need a calculator, it is 324. If I plug in 0, I get 0. So 432 minus 324 is 108. So you can see, I changed the scale here, but you can see, it goes all the way to 180 in the x direction. There's a lot of area under this thing. So the total area between those curves is 108. So we didn't really need the graph, but certainly it can help. And remember, if you're just looking for a way to be able to see this, on a phone or iPad or something, that's a free app. It's also a website. The website isn't quite as nice as the app, but it's a pretty nice way to get a graph.